everyone. Welcome back to my mathematics teaching channel online today. So I would like to continue in this video. I would like to continue with the function and the limits before we move on to the derivative. There are two mini lessons I would like to mention to you. One is about the function, continuous function, and discontinuity of the function, and the average rate of change. So there's, and I will not go into too much detail about this. The lesson online I will upload into my online course when I'm still developing the course online for all of you across the level. And I hope I can help you to understand much better about mathematics. And this, with the pandemic going on, there's a lot of online lesson now. If you really want to learn and you really want to have a, not wasting your time with the silly stuff, and you want to build your future, if the school is shut down or whatever, you still can have access to the internet and you can learn on your own. We call it self-directed learning. And self-directed learning to everybody, doesn't matter, it's never too late to learn. Doesn't matter you are 50 years old, 60 years old, or like 20 years old. And of course, if you're young, it's better, but nothing hurt and nothing harm to gain our knowledge in a in useful way, right? Anyway, I would like to promote a little bit about my course. So this is my URA. In the future, watch out for this. You can type in my name, T-Nancy-S, School Thinkific is the platform for me to develop the course online and come manage slide course. So in the future, if you go to register online my course, you will have access with on the lesson plans, on there is practice assignment and the solution I provide as well. So you can see how do I perform step-by-step solution. I will not post on the solution. I will just choose typical solutions so that you can follow that and working on your own solution for assignment or courses. And of course, when I publish my course online, you will have access to it, and you can ask me, email me, ask me any question, or even phone me and asking about the course. Anyway, we'll talk about that later, but let's get into the lesson today. Today, the lesson, I would like to introduce you to at least one or two mini lesson about the limits and the function. After that, we will get into derivative, but let's see what I am talking about. So on the bar here, right, I'm talking about the definition of a continuous function. Now, a function can be continuous, can has a discontinuity, and can have a essential discontinuity or removable discontinuity. And you will understand this term after I get into the lesson. Now let's talk about the continuous function first. Of course, look at this function here. This is a continuous function, right? You can see that there are no broken, no anything. It just keep going. The arrow show it keep going, right? So this is the continuous function for sure, definitely. Now in math, in the past, you learned what are the continuous function, usually polynomial function, radical function, and rational function can be continuous and can have a discontinuity as well, right? When we see the asymptote or something like that. Radical function, polynomial function, linear function, those are the function keep going and continuous. Now, however, I'm going to show you the picture of what are the function is not continuous. Now, if you look at the example here, right? This function is also continuous, but have a hole in here and have a hole here and here hole. Now, the hole indicates that at x equal 1 here, right? The y equal 3 here is not as it, not as it. So there's no value of y, and that's why we represent by a home circle, an empty circle, right? No darken. The one with darken like that, it means here, if the y value at 4, right? Then yes, the y value at 4 is as it. And the whole like this, it means not including the y value at 3 at all. As well at here, there's a home here, so the y value here at 1, but because of this home, empty circle here, then this y value is not as it at 1 as well. So this is one case of it, a broken, a little bit discontinuity. But however, if we fill in this home, right? Let's say we fill in it, then the function will become continuous, right? From the interval 1 to 4, right? Just from 1 to 4, from the interval from 1 to 4. So this we call a removable discontinuity. Now, what does removable mean? It means this function can become a continuous between the interval from 1 to 4. And you can see the shape, there's just a little hole like that, right? In between them is the function continuous. Now, let's look at the second case. If you look at this function, right? There's a home here, home here, home here, and this function is the two-piece function, right? There's no function in between them. Obviously, this is the broken function as well, discontinuous as well, right? It's not continuous. Now let's look at the interval between A and B. So from here to here. And from now on, we're talking about the interval, the function continuous on the interval A to B, or discontinuous on interval A to B, right? So because the function is keep going, so a very large value. So we're just talking about the, we just pick up from here to here, like a part of the function and evaluate it, whether it is continuous or continuous, right? So if you're just talking about this function, let me change this, okay? So let me change this is A, and let's say this is B. So let's just look at the right function here, right? Now I'm gonna make this is dark. So this is to home. This is also a removable discontinuity. It means if you fill up this value, you give it a y value, then it can be a continuous function, right? In this shape like this. Now let's look at the third shape, okay? Down here, you can see that this is also a continuous function, right? There's no break, right? between the interval A to B. However, at C value, right, at C in between these value, you see that the function have a very sharp curve up here, like the pointed, right? And if the function have pointed like that, is derivative does not exist. If you see it, because what happened is the function go up, 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 and then suddenly go down in a very sharp turn, right? So it caused you know, a curves like that. So anytime you see a curve like this, C-U-R-P-S, I guess, a curves, then you know that this function can be differentiated anywhere, right? From here on way up to here. But at C value, this is no derivative. You cannot get the slope of this pointed here. So its derivative does not exist. Now, once the function have its derivative does not exist, it means the limit, it means this is a, it could be a continuous function, but cannot be differentiable, okay? Another case of a broken function is this case. If you see from the interval A and B here, right, there is an asymptote, vertical asymptote. So these functions go from here and up, 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 cut a y-axis at one point and very close to this asymptote, but never across the asymptote. And again, on the other side, so if you look at the C value on the left, we have this curve, and on the right, from the C value right here, right, on the right, you have this curve. So this curve have an asymptote, horizontal asymptote here, because this function never touch zero, act at zero, right, or y0, right? And here it have an asymptote as well, but it's not horizontal like that, but vertical like that. And this keep going this way, and this one keep going like this, but they're not crossing each other and they're not continuous. So this is another discontinuous, and this we call it essential. It means it's very important, right? Essential discontinuity. Discontinuity. Now, why we make this term is very sound like very technology, very terminology, right? Because in the future, we will have to base on their limit to prove that whether or not the function is continuous like this or broken like this or discontinued. And how it's broken is that essential discontinuity or removable discontinuity. There are conditions we can prove that, but let's give the definition. Now you have in your mind of what is a discontinuous function and what is a continuous function. You have that in your mind already. Now let's talk about what is the definition of a continuous function, right? So let's talk about that after you have seen the picture of how discontinuity means and what is the continuous function is. So here, let's call this function is f of x. So condition for a continuous function. And let's say on the interval A to B, right? Okay. So if this f(x) is continuous function on the interval from A to B, then it has to satisfy three conditions. First of all, let's say if I want to Now, let's say this is C value, right, in the middle of it. I want to prove that this is keep continuous, and I just pick a point between the interval A to B, right? Between this interval. I just pick a point C on this. Now, I can draw the read on here as well, but I just leave it like that for now, okay? So the condition for this will be, first of all, f of C, f of C have to be defined. So the function here, let's say if we look at the C value and we substitute the C value in here, and whatever the function is, we substitute into the function, we find the Y value, right? Because remember the function here, f of x is mean Y value. And C is just one of the X value on the interval, right? Between A and B. So if we substitute the X value in here or the C value in here, and you base on the function, right? Now, right now, I'm not saying what is this function here. I'm not making any function. Just assume this curve have a function f of x. It could be polynomial function. Look, that's the polynomial function, right? A cube, x to the power q plus 2x, something like that, my square, something, okay? So, but we're not bothered to figure out what is that function is. We just want to know how it's continuous and it's discontinuous, right? So let's see how we deal with this. So the definition say, if the function f, we put the value c here and f of c defined. That's the first condition. The second condition will be limit of f of x. When x approach to c, have to be as it equal L, equal a number L limit, whatever number, could be 2, 3, 4, 5, minus 3, whatever, right? So the limit of it have to be as it. Now remember, at this function, limit does not exist, like if it's broken like that, right? At this point C here, the limit does not exist, and the derivative is non-exist, right? So limit of f of x when x is brought to c equals some value as it. And the third condition is say if we plug in the value of c, f of c, right? This one here have to be equal the limit value of f of x when x approach to c and equal L. So let's say after you find the limit, this function, you get the value L here is 3, right? Let's say number 3 as an example. Then when you evaluate f of c, this value have to be equal the limit of it, which is when you substitute the value c in here, you find this value equal the limit of f of the limit of f of x when x approach to c. So if it satisfies 3 conditions like that, then you say that, oh, this is the continuous function. And it's true. Why? Because if it's broken, let's say it's broken like this, then how do you find the derivative of this one? The derivative is just the slope of the tangent line at that point. Remember previous lesson? And if it's broken like that, how do you go and find the tangent line? There's no point here for you to see, right? For you to find the tangent here. And therefore, to be a continuous, you must, this function must be differentiable at the c value. It means you can find the slope of tangent line at the point C here, right? So that's the idea. So to prove that this function is continuous, because we don't draw it on the map, every function. And sometimes if you look at the numerical value and given the function to you, you'll be able to prove that, oh, this is a continuous function or discontinuous function. And therefore, as long as it satisfies these three conditions, we can say that this is the differentiable function at x equals c, and the limit of it as z as well, right? But to find the limit of it as z, you have to look at left-hand limit, right? When the function approach to c on the left, and when the function approach to c to the right, on the right. And we talked about that already in previous stuff. So now, as long as you find out these three conditions, you can conclude that I have proven to you that this is the continuous function. There's no way this function have a whole this broken anywhere, okay, on this interval a to b. Now, so in other words, if you want to prove, so let's talk a little bit about why this one is continuous, but it's not differentiable, right? Let's talk about this one for now. And how do we do this? Now, keep in mind like this. If a function differentiable when x approach to c, right, at the value of c, as the point, when x approach to c, if this is a differentiable function, it will guarantee that this is a continuous function. So you cannot have a broken function at that point and can be differentiable as well. And I just show it to you, right? If we erase that, there's no way you can find the slope of tangent line at that point. So if it's a differentiable function at that point, then it will guarantee that this continuous at that point as well. Now, however, in this case, you can say that on the other hand, the function can be continuous, but might not be differentiable at certain value of c like this, like when we have a curves like this, right? So we will say that differentiable guarantees continuous, but continuous is not necessarily, do not necessarily guarantee the derivative. So just remember that, right? And so I can read this to you, and it's in my note. If a function f of x is differentiable at x equals c, then it is continuous at x equals c. A function can be continuous at x equals c and not differentiable at x equals c. So in this case, I draw the graph here, right? And so in short, we can say differentiation guarantees continuous, but continuous does not necessarily guarantee differentiation. Okay, so also there is a particular thing when you have to prove the removable discontinuous, okay? So let me mention that to you too. So to prove removable discontinuity is mean to prove that limit of f of x exit equal L when X approach to C, but F of C not the same like L value. So how do you prove the removable and discontinuous function like this? And what you do is, let's say you want to find the limit of this function. And of course, the limit of this function is equal to, right, the value of 2. But when you plug in the C value in this function, you don't get the value here at 2, the same. But maybe you get this value here at, let me change this a little bit so you can see the scenario. Let's say you find this value at 4 when you put the C value in here, right? And you can see that there is a gap from here to here, right? If the value of the limit here is equal to, but when you plug the C function, the C, the X value into this function, and you calculate this at 4. So this is at 2, limit at 2, but the Y value, when you plug the C in, equal 4, and you see in the picture, you see the gap here. They're not until if they join together at the same value, like this one, right? This condition, then of course, there's no gap here anymore. And you can see that from the picture, right? Right? So let's say if the limit of this is equal to, and the value as C, when you plug in, this is the same function. Let's say the one function, right? But just to piece like this, but as a one function, then you can see that there's a gap here because the value of C here, when plugged in the C value, the Y value here at 4, but the limit here at 2. So therefore, they're not the same. So by doing this, you can prove that this is a removable discontinuity. So I will show you an example how to prove this stuff. What about if we want to prove, okay, let me give you all the information for this video first, and then in the next video, I will show you the example of it, how to prove it, okay? So let's say, so remember, keep in mind these 3 conditions, right? So I'm going to have to erase a part here and show you how to prove the essential discontinuity. And essential discontinuity like this picture, right? So to prove f of x has essential discontinuity. When x approach to C value, right? Or at x equals C. Or at x equals C. So to prove that, you have to find the limit of function f of x. When x approach to C is the not exit. So in this case, you have to prove the limit here, the not exit. So it means you cannot differentiate, function is not differentiable at x equals C, right? However, but if you plug in f of C, then it's equal a value of k or something. So it's might define, right? So this one is f of C might be define. But the limit does not exist. So as long as you see the limit of it does not exist, then the function have an essential discontinuity. However, if the limit exists, but the f of c is different from the limit, then it's the removable discontinuity. Removable discontinuity. And we draw the picture of like this, right? That's a removable discontinuity. Removable. Okay? Now, keep in mind this condition, and I'm gonna end the video right here so that it's not too long and not give you so overwhelming information. And see you in a minute when I show you the example of how to prove a continuous function as well as removable and discontinuous function. Okay, so bear with me for the next minute to the next video. Bye for now.